Afternoon, or good morning, depending on where you are in the world. Welcome to this webinar on raft and soil structure interaction, Pdisp and GSA. We're looking at Pdisp and GSA building, well, GSA building, GSA suite. GSA is the raft aspect of GSA, which is available externally to non-Arab customers in the form of GSA building. It's a quick overview of the functionality. If you want to go into more detail, then we can do that at a later date. I mean, there is questions and answers at the end, but ask questions then and ask more questions later. Do please. So, enough preamble. Soil settlement and soil structure interaction with Pdisp and GSA. Is it a problem? Can be. This example, bit of subsidence hitting that house rather badly. Maybe an extreme case. I mean, more common on sort of masonry structures in general, bit of ground movements, differential settlement, so on. A lot of cracking. My old boss used to tell me that masonry cracking was okay as long as you couldn't put your hand into it or see daylight through it. And I think this crack definitely counts as being a problem one. It's not always a problem if the ground is considerably stiffer than the structure, or if the structure is considerably stiffer than the ground. But where you do need to worry about soil structure interaction is when you've got the ground and structure of a similar stiffness, and maybe you've got sensitive structures to movement, large glass facades, raft foundations, moment frames, and so on. So how does Pdisp and GSA work? Well, it's a combination of two programs. The first one is Pdisp, Pressure Soil Displacements. It's one of our geotechnical programs, which gives soil movement under load. Uses two methods, Pdisp and Mindlin. Each have their advantages and disadvantages. For example, or strengths and weaknesses. For example, Pdisp gives stresses and displacements in soil, but it's a little bit more sensitive to how you set the model up. Mindlin, on the other hand, just gives displacements in the soil, but is much more robust and has the advantage that you can model piles in there because it can deal with shear loads as well as just pressures. Now Pdisp is combined with GSA, which is our structural fundamental analysis program, which does many different types of analysis, but the one in particular we're interested in the soil structure interaction. Now, so this combines GSA and Pdisp. It does a soil structure interaction which is a vertical only for rafts and vertical and horizontal for piles, or of course a combination of the two. Has both the Pdisp and the Mindlin ground methods in there. Pdisp is only suitable for rafts, Mindlin is suitable for rafts and piles. And it is an iterative process, which means there's some amount of cycling going on. So what it does is that GSA will assume a spring stiffness anywhere on the structure where you tell GSA that it's going to interact with the ground. It makes a default guess, which you can adjust. Closer this is to the final stiffness, the quicker it will converge. Now, with these spring stiffnesses supporting the structure, it'll then do a static analysis, and at each spring location you get a reaction because it knows the soil interaction area. You get a soil pressure, and of course because it's a spring you also get a displacement. Now the soil pressure is then calculated and compared to the max and minimum values that you've specified. Minimum values typically 0, which will allow the structure to lift off the ground, and the maximum value which will simulate plastic yielding of the soil. Then these soil pressures are then passed into Pdisp to get the soil settlements, and with these soil settlements and of course associated soil pressures, GSA can now calculate new spring stiffnesses from those results. And the whole thing then cycles round until the two have converged, i.e. the two values are close enough together. The soil data in both Pdisp and GSA are defined the same way. You have one or more soil strata where you define the top layer of the soil, and each soil layer has its Young's modulus, which you can specify a different value at the top and the bottom of the soil, and you also need to specify the Poisson's ratio of the soil. Busenest method has one constant Poisson's ratio for everything. Mindlin can have different Poisson's ratio for different layers. You also need to have the rigid boundary level, which is the limit of the problem at the bottom. This can be bedrock, or it could just be limit of the model, the soil stress bulb underneath the structure, because you don't really want to analyze all the way down to the mantle. With these soil profiles, you then assign their location in space and call it a soil zone. Now these soil zones are rectangular, which means if you need complex areas, you need to have several which overlap. Wherever soil zones do overlap, GSA will take the soil zone with the higher number, and thus you can achieve some quite complex strata results, strata arrangements underneath the structure, but obviously a lot of this will depend on the sophistication of your site investigation. I mentioned about springs. Now, in the model underneath the raft, you will have a number of vertical springs, and on the piles, whilst it just shows a single spring, you'll actually have multiple springs there, because whilst the raft only deals with vertical stiffness, the piles are dealing with multiple stiffness types: skin friction on the piles, lateral loading resistance, end bearings, and so on. So every node on the pile is connected actually by 3 non-linear springs to give these soil properties in the 3 directions. Now, these are non-linear springs, but the soil is elastic. The static analysis is elastic, but it's a non-linear method overall. Now, these springs are derived based on these get the, of course, settlement from the interaction forces. So the interaction force on a pile will be function of the stress times the area, same as the interaction force on the underside of the raft. But with piles, the contact stress is not just force over area, but it's this coefficient C times the soil strength, and this coefficient C is a function of the relative displacement between the piles, so the difference in displacement between the piles and the soil at a particular point, and the dimension of the pile itself. Now there are a number of guides out there giving suggested values or formula for these, and you can include these, well, you can these coefficient results into GSA. So let's see this in action. Let me start up GSA. And the first thing to note, in your preferences, you've got to make sure that you have the raft aspects activated. Always helps, and I will just go and create a raft. I'm going to create a raft using a manual mesh. So I'm just going to add in some nodes. Oh, and I'll set my default Z to be -1 meter, and I'm going to do it 20 by 30 meters. So there are my 4 points, and I'll just draw in a quad element in there. Now, this quad, of course, is far too large, so what we need to do is break it down. Now, I'm going to do some meter thick raft, so I'm going to break it into 2 meter square elements using split quads. So that's going to be 10 by 15. Yeah, that's good. So, raft properties itself, I'll make it as a shell, say long-term concrete, 1 meter thick, and the benefits I'll take into account a bit of cracking and so on. Make it 925 thick, but make sure it's 925 millimeters and not percent. Otherwise you will find your raft is a bit stiffer than you expect. Don't need to worry about the other factors. And that, let's have a look. That looks about right. Okay, let's put some loads on this. Let's give some names first. So self-weight and building loads. So the self-weight is going to be just the self-weight of the slab, but the building, rather than modeling the building itself, assuming it's a flexible build structure, I will add a number of points on here, which will be the columns. There's nope. Asymmetrical is 50. Asymmetrical. Never mind. So these will be my points, and I'll just create nodal loadings on those. Let's say 1000 kilonewtons. Obviously, you need to put in your correct values rather than my generic ones. Self-weight and load. Now these this raft will need to interact with the soil, so I'm going to select all those nodes, and now then, let's set the raft properties. Actually, before I do that, what I'll do as well, because the raft is vertical stiffness only, I'm going to just pick a point in the middle and just restrain that so the raft can't translate, and I'll pick a point over there and modify that and give a stiffness in the Y direction so it can't rotate. These 2 points together shouldn't attract any reaction, but they'll just give a stiffness to the analysis. So set up the raft. We've got raft section down here, and we've got the raft specification. The raft specification main thing is setting the rigid boundary level. Now I'm taking 0 as being the ground level. That is one option, or you can take actual site levels. There are some other options in here about the actual workings of the analysis. Something for you to decide based on your own experience. And we need to interact this raft with the ground. So open the raft interaction table. I'm going to select these nodes here. And I'm going to copy as list, paste those node numbers in. Now the dimensions, the plan dimensions are fine. Let me just tuck this up the top. let's look at the raft interactions. Because GSA knows what elements those nodes are connected to, and therefore can work out the interaction areas. And you can see they're full 2 meters squared in the middle, and 2 by 1 on the edge, and 1 by 1 in the corners. But the levels, if the centroid of this raft is at -1, so the interaction level is actually going to be -1.5. Also got the maximum minimum pressures in there, so I can allow the raft to lift off the soil, but with such a large maximum pressure, I'm not going to worry about yielding with the soil this time round. So the soil itself, and the soil profiles. So level top 0, number intermediate displacement levels. I'm going to use Mindlin method throughout, so I don't need to worry about displacement levels. That's a Boozenesque thing only. And I'll set the stiffness of the top strata and roughness ratio, and I'm not worried about the nonlinear curves or pile soil properties at the moment. I'll come back to that last column. -10, and make this level a bit stiffer, and then -20, a bit stiffer still. So that's the strata, and I'll then say where in space the strata goes. Now, obviously the soil needs to extend beyond the raft. How far beyond? Certain matter of conjecture, might need to do some experimentation. A reasonable rule of thumb is to take it beyond the structure, distance equal to the depth of the ground below the structure. So, as it's got depth of 30 meters, I'm going to take this 30 meters beyond, and it's 20 meters wide, so that goes to 50, and then in the y direction, oops, and let's have a look at that and switch on the display of the soil zones. And that looks pretty good. And you'll note that the raft is below the top of the soil, but we're raring to go. Now, if I've remembered everything, this should be suitable for analysis now. So let's start up a new analysis, which is going to be a raft analysis. Use Mindlin. This is the convergence criteria. The smaller you put this, the longer it takes to converge, the more accurate results. You might find if you set this too tight, you might struggle to get a convergence, but 0.1 should be okay. I'll add in my self-weighted building loads. Obviously these can be factored if you want. I'm assuming the building loads are already factored, and do things like show the stiffening contours, and most usefully you can save the soil stiffnesses as support springs. What this means is that the analysis will find spring stiffnesses at those nodes, and ticking this will mean when you delete the analysis results, you'll still have those spring stiffnesses assigned to the model. This means that if you run that model a second time, it will be a lot quicker. Also means that if you want to run a similar loading on the raft, then you don't need to rerun the raft analysis. Now I mentioned about spring stiffness. Let's look in the advanced settings here, and under raft there is a default damping coefficient which I find about 50% works quite well. Sometimes the numbers can jump around a bit, and this is the initial support stiffness as well, which in my experience probably about 10 to the 1 to the e to the 4 is closer than 1 to the 7. All this number does is, closer this is, the faster the convergence, that's all. makes no difference to the end results. No preload. I want all the results. 2D elements. That's all good. Stiffness. The new sparse parallel direct quicker analysis. So let's analyze that and see what we get. And we can see the numbers are going down and it's converged. Wonderful. So what have we got here? Let's tidy this up a little bit. Let's switch off those interaction areas and switch off the supports. So you can see the deflection there. Let's have a look at, let's say, 2D element displacements. And you can see that the rafters deflected down about 10 mil at the edges and close to 30 mil in the middle. Let's get actual values. Okay, 11 to 25 mil. So you get differential settlements across the raft, which is what you expect. This is because let's look in the plan view here. The stiffnesses of the soil underneath each point increases as you go towards the edge. Now you note that in this case it drops off at the very edge because these nodes have got a smaller contact area and therefore lower overall stiffness. But it does mean if we look at the soil contact pressures, it means the contact pressures is relatively low in the middle and increasing towards the edge and especially at the corners. Now we can also display these nodal results on the 2D elements as well, and so we can then get a contour diagram of the results, so it can be easy to see what's going on. Now that's a nice regular raft. What happens if you've got something a bit more irregular? Now I'll quickly show you a auto mesh. Now I've got a separate webinar recorded online which looks in more detail at the modelling of these sort of rafts or meshes and so on. But I'll quickly show you how to do it here. Let me just change it onto the design layer. The design layer means where I can define the mesh, and I'll define the mesh using these add lines, and I'll just put something in reasonably random as a loop, so add an area, and these lines will define the nodes going around the edge. So let's see those, and I also want to add in some additional nodes on there which are going to be my column nodes. Now if I just select those and select the area, then right click to add a region. So it picks up those nodes, picks up that area, and this region will then be what is meshed. Now there are various options here that you can play with. The one I'm most interested here at the moment is one called Create Soil Spring Supports per Generated 2D Elements. What this does is, rather than interacting each corner node, what it will do is it will create a node in the middle of each mesh, which then tied onto the surface of that mesh with the appropriate interaction area. So you can see there's that mid node in each of those. And if we look at the interaction areas, they've all been calculated for us automatically. Now let me just delete that mesh a minute. Now at the moment these the moment those nodes that we chose are tied topologically into the mesh, they're actually at the corners of the elements. So what I'm going to do is I'm just going to delete that mesh at the moment, and I'm going to edit that node attribute and say I'm going to tie it to the mesh, and I'm just going to set my defaults as that, so I can then use this tool to apply those other defaults on. Now what this means is that when the when it meshes now, you can see that those nodes are on the surface of the mesh, not at the corners. This means that the mesh generated is a bit smoother, give a better result. But the principle is the same. And if you want to add these solid interaction nodes to manual mesh, then you can just use this contact constraints tool to create those points. The analysis is exactly the same. Now, this is just a straight raft. What happens if you want piles? The piles, let's pick some points to interact. I'm going to pick some points for those piles, and I'm going to create those piles using extrude commands. Let's say 8 increments minus 2 meters, so 60 meter long piles, and include beams. So these piles need to interact with the soil now. So I just copy those as a list and go to my pile interaction table. I just paste those in. This time I will take the automated dimensions and elevations for these piles. So what this will do, if I just switch the soil zone off for the moment and the pile interaction area is on. Aha! No areas until I tell it that it is a 600 pile. Haha. Circular. That's better. So you now get these interaction areas with the raft, which correspond to the structural dimensions of the elements themselves. Now, these are interacting with the soil, but we're not telling it how yet because we need the pile-soil interaction coefficients. Now, I've got some numbers which I've grabbed earlier from the API document, as it happens, and so I'm going to just copy these over and create these curves. So this is the TZ for shaft friction, and then we have the tip or base QZ, and finally we have the lateral PY curve. We assign these coefficients into a pile-soil interaction property, which I'm going to call clay, because these are all clay curves, and the lateral ones brings the PY curves, the sides, and the base, and the maximum soil pressures. Once we have these pile-soil interaction properties, we can then go and define them in the strata. Now, note we could have another table, and put a different one in there, and so you can create many different pile properties and so on. That of course is blank, so I don't want to use that, and just take it out so it doesn't complain at me. Right, with this in action, the analysis is exactly the same. Takes a little bit longer. These piles on reaction curves are quite non-linear, and so what I'm going to do is I'm going to say, here's one I prepared earlier, which has been analysed, and we can see we get things like the contact shear stress down the piles, or let's smear that on the piles, and we still get the contact pressures because both the raft and the piles are working together. The pressures hopefully should be a bit lower on the raft now. You also get things like the moments on the raft, forces, axial loads on the piles, bending moments on the piles, and so on. Everything you need for the detailed design thereof. Now, I mentioned about Pdisp. This data in here, this is all exactly the same as Pdisp, and you can indeed import the soil data from Pdisp, and you can also, once you've done analysis, export out to Pdisp. And let's put that onto my desktop there, and minimize this down, and let's fire Pdisp. Let's have a look. I can open up. There is my piled raft. And in here, if I switch on to the wireframe, we've got all the various loads on there. Let's just label those for the moment. We've got loading arrows and so on. And we can analyze this and add in displacement zones and so on, and get movement in the ground below. So let's let me see. So a grid, let's say that'd be minus 30, let's say at minus base of the raft. The second point will be 50 and minus 1.5, and say 20 points across, and it needs to be then up 30, 60, 90 meters. I think another 20 points. Calculate, and I'll do another one. Oops. A lot further down. So, got them reasonably right. So those are my two displacement grids. Okay, numbers are it's a bit wide. Never mind. Yes, wonderful. And if we're to analyze this, just calculating, and we'll then be able to see ground movements below. So while it's thinking about that, let us return to the PowerPoint and say let's have a look at software in action. Well, I've just got the one case study. Now this case study is available on the website, but I thought I'd draw it to your attention because it's quite an interesting one. It's the Aspire Tower in Doha, in Qatar, was built for the Asian Games back in 2006, as it happens. 300 meters tall, and the whole superstructure was designed in GSA, but also important thing today, the substructure. Now, this is their piled raft. They use a grillage rather than 2D elements. Grillage is another option for rafts. Generally these days, 2D elements seem to work quite nicely. Also got an axisymmetric analysis through the depth of the raft, so you can see how the stresses flow through the structure. Now, so this raft is restraining both gravity loads and also wind and seismic loads and everything. And there is more details online if you have a look at the case studies, Spire Tower, and I think you find it of interest. Now, if you have any further questions, contact us at oasys@arup.com. Go for more information on the websites, both on Pdisp and GSA building. There are some sample models which are applied with the software. Any further questions, just let me know. Contact me through that address, or if you've got my address, you should have it directly. And thank you for attending. I hope you found that useful, and I look forward to seeing you again.